whole session, and we'll be helping you to coordinate between you and the instructor and helping you with all your assignments and questions, and so that you can take this course easily. So myself, Shubham, I'm the representative of Robotics Club IIT Ropar, and we have here 5 more coordinators who will be helping us throughout the course. I'd like the coordinators to introduce themselves. Thank you.
Hi everyone, I'm Vedant, a second year undergraduate from Electrical Engineering.
My name is I'm a second year electrical IIT Ropar.
Hello guys, I'm Vedansh, a second year electrical undergraduate. Feel free to message any doubt if you have.
We have 2 more coordinators, so they are not present in the meeting, but they are actually the teachers in the classroom. You can contact them over email, and feel free to connect with us over LinkedIn, and do make sure to follow our social media handles on Instagram and LinkedIn. So, yeah. So now Mrs. Akshay Mahana will be taking over. He'll be starting the session. So over to you, Akshay.
Okay, so hello everyone and welcome to this ROS Learning Series. This is going to be a 6-part based series and we are going to learn about robotic software and ROS. First up, I would like to thank the members of Robotics Club for organizing this series and having me as the speaker over here. So if you have been following my YouTube channel, you may know about me, but since there are a lot of new people over here as well, let's just start with an introduction. So who am I? Hello engineers, I'm Sakshay. I am a final year undergraduate student at IIT Ropar. Apart from my studies, I have a YouTube channel that goes by the name Robotics with Sakshay, where I put videos related to robotics and artificial intelligence. Now, I have done various internships in robotics and ROS, and one of my project in ROS was also selected as a lightning talk in ROS World 2020. Now, ROS World is a renowned conference in ROS where people present their work that they have done using ROS. So why I teach robotics, why I have this YouTube channel, and why am I taking this series? It's just to learn more about robotics and share all the experiences that I have. So enough with the introductions. Let us get into what is ROS. Now this first session is completely going to be an introduction and installation part as such. So it's going to be really light in theory and the demos as well. So let's go. What is ROS? Now ROS stands for Robot Operating System. Now in very simple or bare minimum terms, without going into many technical details, ROS is just a collection of open source software that is used that helps to create robot software. Now robot software can be anything ranging from very low level like device drivers and even from a high level like we can say computer vision, motion planning, and so on. Now the name of ROS stands for ROS Robot Operating System, but it is actually not an operating system. It is just a set of software libraries that run on top of a Linux operating system. So we can install ROS. To install ROS, we first need to have a Linux system, and we can install ROS or all the related software related to it on that Linux operating system, and then use it to build robots. Now, I also mentioned a term over here, open source software. What open source software means is that it is a type of software whose code is publicly available for people to read. So people can go online, read that code, and even make changes to it with permission to the creators and maintainers and improve the code base. Now, that is the complete philosophy of open source software. And ROS is an open source software itself, as it is a collection of open source software. Now, why should we learn ROS and what it encompasses? So let's discuss that with an example. And also, in case you have any doubt while going through the lecture series, even in the further sessions as well, just feel free to put that in the chat, put your question in the chat box over in Google Meet, and I will address that question over there. Okay, so first we will start with a quiz over here. Now, I'm not going to ask which movie is this, but I'm going to ask what is the name of the robot that is present in the middle of the screen over here. So here to you can put your answers in the chat box for that. Okay, so so Soumyadeep replies dummy. Okay, Gushan says Jarvis. So actually this robot is serial manipulator. Okay. So there are a lot of answers over here. This was not like a technical question as such, just the name of this robot in the movie. And in the movie, this robot is called Dummy. That Rohan, Soumyadeep, and Vinay have answered this over here, Dummy. Now, this is as someone over here also said, Ajay Adit, serial manipulator. It is a manipulator robot or a robot arm. Now, in the movie, this movie is, by the way, Iron Man 3. And in this movie, this robot is shown to be quite intelligent. Like, it can take audio commands from a user and do the work that the user has commanded it to do. Like in the image, we can also see that the person over there is asking the robot to clean some space, and the robot is going to do it on its own. Now, let us, to understand why we need to learn ROS and why is it so important, let us use this robot as an example. Now, let us say that we want to construct this intelligent type of robot that can take in audio commands and do all the commands that we ask it to do. So let's see how we can do that. Now, robotics can be, generally people say that robotics can be divided into 3 sub-disciplines: mechanical, electronics or electrical, and computer science. Let's just go on with this definition that people use, and let's see how we are going to build this robot over here. So the mechanical part of the robot is going to handle the structure part as such. We are going to discuss them one by one in the further slides, but just as an overview, the electronics part is going to handle the communication, and computer science part is going to handle its intelligence. So let's see what these terms mean one by one. First is the robot structure. Now, robot structure is the mechanical construction of the robot. Let's say that we want to build a robot that has to work in a nuclear kind of environment, nuclear power plant. So for that, our robot needs to be made in such a way that it is resistant to radiations. For instance, if we take another example, that we want our robot to be able to clean spaces that are tight spaces and be able to clean them. In that example, our robot body needs to be long and slender, and so that it can reach tight places. If we have heavy load lifting tasks, then the robot also needs to be sturdy and so on. So based on the environment it is going to work in, we need to design a robot in such a way. So mechanical part or the robot structure handles this design part of the robot. So all the physics-based things come in this category over here. Okay, second is the robot communication. Now, robot communication is it enables the robot to interact with the physical environment. Now, for instance, we can see the photos over here of motors, sensors, and cameras. Now, the motors of the robot are going to actually be able to move the robot so it can interact with the things that are present in the environment. The sensors, like a sensor in the robot motor, is going to tell what is the position of the robot in space. And likewise, the camera or even the microphone sensors are going to tell it how to receive the commands from the environment. So, like, taking all these things into account, the communication part is handles all these things, how to perceive and interact with the environment. it is also something very similar to how a human body works. Well, like for our arm, we can say all these are somewhat motor joints, and our eyes or senses are just cameras and microphones as such. So we take in commands from these and output these commands in the form of motors, like moving our hands and so on. The third part is the robot intelligence, and this is also the part that we are going to focus on for this series, since ROS is used to build robot software. Intelligence part is once we have all the inputs from the different sensors, from the different motors and so on, now we need to process those inputs and tell the robot, and the robot then needs to decide on its own how it is going to do that task. That is comprised of intelligence. Now, if we build, let's say, from the previous two phases, we have a machine that has all the electronics fit into it and the mechanical structure. And if we create a remote for that machine, that is simply a machine that can be controlled by humans. But to actually make it a robot, we need to provide software or intelligence to it so that it can take its decisions on its own, how it is going to do that task. So from the okay, so software part, it's what comprises the intelligence part of the robot. Now, as I said, the ROS is used to build robot software. So let us dive a little bit deeper into how this robot intelligence, like how is the software. Let's dive deeper into the different types of software that we have for robots. First is the low-level software. Now, once we have all the motors and all the sensors connected to a, let's say, CPU, and now we are assuming that we already have a robot, like the complete mechanical structure and the electronics that we have. Now we need to find a way to control those electronics and sensors autonomously. So let's say we connect the motors and the sensors to a CPU. Now, mostly these days, the motors and sensors that are available, they work on digital-based commands. Digital commands are streams of zeros and ones that a computer can interpret. Now, directly connecting the motors or the sensors to a CPU is not going to give us any results as such. We need to process those digital values and create a we need to create a tangible value that we can understand and process it as such. For that kind of software that operates at this low level of hardware software interface is called a device driver. Now, most of the times, the hardware manufacturers that we have, they already provide us with the device driver that we can install on our computer and use the device that we have. But even sometimes there is a need that we need to build the device driver on our own for our particular use case or our particular computer. So that use case also arises. So let's assume that we are done with the device drivers. All the motors can be controlled, all the sensors can be used. Next comes up the high-level software. Now we have taken these commands from each of these inputs. Now we need to process these inputs and finally give out a command to the motor to move accordingly. So this forms the high-level software. All the popular algorithms like motion planning algorithms, computer vision, and so on come under this category of high-level software. Okay. So let us say that, so these are all the technical discussions related to the robotic software and hardware that we have. Now let us come back to the example that we had, that we need to design this robot. So let us consider a use case over here that we want to serve drinks to our guests and we ask our robot dummy to do this. So how we would need to program this dummy to do so. Let us see that. Okay, so once we provide an audio input, let's say serve the drinks, the robot needs to understand that audio command. It's going to take the audio value from the sensor, but it needs to understand what was being said. So this part of the software that is going to handle this is called audio processing. Next, the robot is going to be standing near a kitchen counter where it is going to hold the glasses and the drinks. So for that, we first need to process the image input that we have, what is present on the table, and move the things accordingly. So for that, taking information from an image is a subfield of its own called image processing. Now, when the robot has analyzed everything that is present in its environment, then the robot needs to plan its motion. It needs to take its hand and um, hold the bottle and pour the drinks in the glasses. Now, the robot needs to move in such a way that it avoids breaking things and touching other things as such. That part of the software is going to be handled by what is called motion planning. So let's say that for the software, we need to take care of these three different kinds of domains: audio processing, image processing, and motion planning. Now for audio processing, all these three things that we discussed, all these three topics are subfields of their own. And there exist a number of different algorithms for these three topics alone. If we consider a robot that has to do another task, then there is going to be another different subtopics as such. Now for audio processing, we have a lot of different algorithms. Let's say that we are operating the robot in a silent environment. Then a simple audio processing algorithm would work. But if it is operated in a noisy environment, then we need to use a more complex audio processing algorithm. Similarly, for computer vision or for the image processing part, if the kitchen countertop is very cluttered, then we need to use a sophisticated image processing algorithm. If it is relatively empty, then a simple algorithm would also work. And this goes for the same for the motion planning algorithm as well. Now, for a person like us that is building this kind of robot, dealing with this huge amount of software is really difficult. Like, let's say that we were not even given the device drivers for the robot. Now, first we need to write the device drivers. Then we need to write audio processing algorithms, test which one works for us. Then we need to write the image processing algorithm, test which one works for us. And then we need to write a motion planning algorithm. Now, this is a tedious task. Since robotics is a multidisciplinary field, doing all this task is very difficult for a single person. Let's consider an example of a researcher as well. Like, researchers usually work in one particular field of study. Let's say they want to work on a motion planning algorithm. They want to devise a new motion planning algorithm that works on a set of constraints. Now, if they take a robot over here, they want to write an algorithm that does this audio processing, image processing, and then does the motion planning. It's going to be very difficult for them. They first need to write the device drivers. They then need to take a audio processing algorithm, then take an image processing algorithm, and then they can come on to the motion planning task. This was now, due to this, they will spend months of their time building the other algorithms, and they will come to the actual part they want to work on very later in the phase. This is the actual problem that was faced by robotics of times before ROS. And this is the problem that ROS solves. Let's see over what ROS provides us. So ROS basically comprises of 4 different subparts. First one is the plumbing part. So the first thing that ROS provides us is a software architecture. Now, what it means by software architecture? Now, writing a single piece of single file of code is very easy. We can simply import the different libraries and run that code. But for a code that has huge number of components that are communicating with each other, that has a lot of different dependencies, different libraries, and there is a lot of code that we can change, and we have to handle that. And that is a real software engineering problem. For a robotic system, this is the case. We have a lot of different software, low-level software, motion planning software, image processing software, and so on. So what ROS does is provide us with a general software architecture that we can use in our robot. This general software architecture, whatever robot uses ROS is going to have this general software architecture. What this provides us with a plug and play type of solution. Like, we can simply take in the architecture, make some changes that are relevant to us for our use case, and then use the complete architecture for our work. The next thing that ROS provides us is with tools. It provides us tools like for simulating the robot, for visualizing the algorithms that are running on the robot, and so on. So we don't have to build any simulation software of our own. we can simply use the default ones that are provided by ROS, and we can test our algorithms on that simulation. Next, ROS provides us with capabilities. Now, the previous example that we discussed, that there are different algorithms that have to be developed. ROS provides these general algorithms as ROS packages. Now, let's consider the example of a researcher that they want to work on the motion planning task. What they can do is import the ROS packages for audio processing, import the ROS packages for image processing. Now, after importing the packages, they can build their motion planning algorithm as such. So what ROS is providing over here is a pre-built solution for the commonly used algorithms. Even for us, when we want to build the dummy robot, we are simply going to use the ROS packages that have been provided and code that into our robot, and we have the robot working. Next is the ecosystem. Now, ROS is used by a lot of people now. Like, we can ask questions that related to ROS and its components from the maintainers of the project and even the creators of the project. So ROS provides us with an ecosystem where we can solve doubts and ask our questions as well. Okay, so before moving on to the applications of ROS in different areas, if you have any questions, you can let that know in the chat section below, chat section over here. Plumbing. There's a comment over here, plumbing. Okay, tell me once again. Okay, so plumbing. Okay, so when we are writing a big software, like let's say, when we are writing big software, there are a lot of different components that are interacting with each other. There is going to be a lot of message passing from one place to other place and so on. Now, writing this complete architecture that handles all the different, like for example, let's consider the robot example. Over there, the low level software that we have, that needs to be operated in such a way that that is compatible with the operating system. Now, for the higher level software, first we need to do audio processing. Audio processing then needs to give this command to the image processing algorithm, and the image processing algorithm has to process that and output their outputs to the motion planning algorithm. Now, this complete set of communication that is happening is also a part of the software that we have to develop. ROS provides us with a general software architecture where we don't have to write this message passing like this. We can simply plug and place the algorithm that we want to use and get our task done. So it provides us with an architecture that we can directly use. Can we use different without generating it from scratch? Okay. So the next question we have is, can we use different available ROS code and integrate them together like blocks without actually writing that from scratch? Yes, that is exactly what ROS packages provide us. There are, like, if we, let's say we want to write a motion planning algorithm, so ROS is going to provide us with a package and some parameters that we can change that are relevant to our robot. Parameters like the robot size, robot width, and robot height. We can change these parameters and run the algorithm for our particular use case. So ROS provides them as packages. And yes, we can integrate them like blocks. Then we must have Linux system or we can install. So for the installation, there is a demo part of this session as well that we are going to be covering towards the end of the video. So stay tuned for that. Can we run ROS projects on Arduino or only Raspberry Pi? Actually, ROS only works on Ubuntu or Ubuntu-based Linux-based systems. So it can only work on Raspberry Pi. But for Arduino is it doesn't actually work on Arduino. We have to like Arduino works like a sensor for a ROS system. We can connect it to a Raspberry Pi system and we can take in that commands that are coming in from the Arduino and send some of them to the Arduino. We cannot directly run ROS on Arduino as such. We do not need any other platform except ROS for writing the intelligence. Does it comprise everything? Yes, like if our use case, so Tanmay asked, we do not need any other platform except ROS for writing the intelligence. Does it comprise everything? Almost. Like for building a general robot, everything is provided by ROS. But if we want to create something specific, then we have to use some other software. But generally, we can use ROS that can work for any kind of robot software. So are there any pre-trained models available on ROS as well? Like if we want to use a deep learning kind of thing, then the complete architecture of the neural network will be provided in ROS package. Then we can use the pre-trained weights that are available online on other websites. I don't really think ROS package provides them as such, or maybe it does, I'm not sure. But if we have a deep learning based system, then we can download the architecture from the ROS package and use it, use the pre-trained models that are available in other places online. Okay, so which languages are used to write code on ROS? C++ and Python are the main ones that are used to write code in ROS. And difference between ROS and C++ or Python: C++ is faster, and C++ is a bit faster, and it is generally used in real-time systems. Python is a bit slow, and it is generally used if we are like testing our algorithms as such. They are not to be used in real-world environment or so on. Generally, the code that is working on robot is written in C++ due to its speed. Python is preferred when we are doing something in simulation as such. So that's the thing. So for the last question, I think Robotic Club can answer that. And let's go to the next slide now. Okay, enough for the questions. Okay, so let's see some applications of ROS now. Where is it used? Now we have understood what ROS provides us and why should we learn it. Let's also discuss some use cases where ROS is actually used. First is a space-based application. Now NASA in 2012 introduced a robot called Robonaut 2. Now the photo over here is not of Robonaut 2. Robonaut 2 was a humanoid robot that was sent to the International Space Station in 2014, and it used ROS in its system. Even from that time, NASA has used ROS, some components of ROS that they use in their robots that are sent to space. For example, there is a project in NASA, Viper, I think Viper. They plan to send an autonomous robot to the south pole of the moon. In that, for their driving and landing capabilities, they have used certain components of ROS 2. Now we are going to discuss what is the difference between ROS 1 and ROS 2. Let's just say for the same that there is a single software ROS that helps us write the software. So they have used certain components of ROS 2 in that they are going to, or they have used certain components of ROS 2. Next up is the defense part, and what, okay. So the DARPA Institute is a just like in India, and since I'm seeing a lot of people of India over here, since they're okay. Now the company DRDO, it is Defense Research Development and Organization. It develops defense technology for India. Similarly, there is DARPA. Now I don't remember the full form, but there is DARPA that develops technologies for the USA military. Both of these institutes used ROS when they provided challenges for the students to solve. Like they have different competitions. Both of them have different competitions that allow researchers and students to contribute their expertise on those challenges. So both of them, for their virtual phases, generally use ROS. Now for the DARPA one, there was a challenge called Sub-T challenge. Its virtual phase was conducted in ROS. Now DARPA also conducted different other competitions as well, like Subterranean challenge, Urban challenge, and so on. So there was one challenge, Sub-T challenge, that made use of ROS in their virtual phase. Even DRDO is using in one of the virtual phases as well. Next is the warehouse robotics. Now the example over here, okay, Amazon Robotics, which is a good, very popular, I think, company that is related to the warehouse robotics kind of stuff. And even Wipro, the company Wipro, that has a robotics division that works on these warehouse robots. Almost all the companies almost all the companies that we have of warehouse robots generally use ROS. Now, specifically, they use ROS 2. Since ROS 2 has very good capabilities of swarm-based robots, multiple robots coordinating with each other, they have very good capabilities for that. So both of these companies make use of ROS 2 to build their robots. You can see this when you see their application portals. They will usually have a requirement of ROS or ROS 2 as such. Next is teaching and academics. So in the academics research, ROS is very widely used. Popular algorithms like Chimera VO, A star, RRT, and so on, all of these are provided as ROS packages. Even when researchers that are working on algorithms related to robotics, they usually also publish a ROS package for the same. Hence, it is quite used in academics as such. Even in teaching, I could take my example that on my YouTube channel, I'm currently working on a playlist called Motion Planning for Robots. Over there, I use ROS for the different simulations and visualizations. Now, the thing why I use ROS is because a lot of things are available to us directly. We only have to make certain small changes that are related to our work to make the complete simulation for our own work. So it's widely used in teaching and academics as well. So the key point that I would like to take you all to take away from this, that every robot company uses a system that is similar to ROS. Now, let's say, for example, Tesla and Boston Dynamics. These two are very popular robotics companies that we know. Both of them use a system that is very similar to ROS, but not actually ROS. They use a system that is very similar to ROS. Now, ROS, this is because of the software architecture part that we discussed. The message passing system that they use is very similar to how ROS works. So motivation for learning ROS is not just as a tool, it should also be as an architecture of how it works, since it will help us develop systems that are related to robotics. Okay, so we are in the demo part now. Before starting the demo part, if there are any questions, you can ask them in the chat. Okay, so let's start the demo part then. So there are two versions of ROS as we discussed before, ROS 1 and ROS 2. ROS 2 is a newer and improved version of ROS. But why are we not learning it? This is because of the availability of resources and the help that we have for ROS 1. ROS 1 is a well-developed project and there is a lot of support available for it online. Hence, for learning the concept-wise, both of these softwares are quite similar. Hence, we are going to use ROS for this learning series. And we're also going to have an introductory session on ROS 2 towards the end as well. Right. Now, as I said before, that we need a Linux system for ROS to work. So to overcome that issue, now a lot of people are going, a lot of people like me are going to have a Windows-based system. And some people may also have a Mac system. It is quite, I won't say, it would be quite uncommon to have a Linux system already installed on your laptop. So we are going to use a third-party software for that called Docker. So Docker is a very popular and very important software used in software companies. What Docker allows us is to replicate the environment in which a software is running on somebody else's computer. Let's say that I am working on a software on my computer and I have built, then that is a very large piece of software. Like there are a lot of different libraries that are being used, a lot of different dependencies and so on. To make that, now usually in software companies, there is one working team and there is one testing team. Now for the testing team, once the working team has built the software, they send it to the testing team to test it. Now for the testing team, it is quite difficult that they first need to install all the libraries, all the dependencies and so on. And it is very likely that they are also going to have been running a different version of operating system on them and the dependencies are not going to match and a lot of issues can arise. So Docker helps us with unifying this environment. it actually runs a kind of virtual environment on our computer so that the complete behavior of the software is replicated. Hence, we are avoiding the installation of ROS by simply installing Docker. Now, also the instructions that we're going to discuss will be in the slides over here, which will be shared. So for the instructions, you can either follow along or you can listen carefully and then try them on your own by using these slides. Okay, so let's start with the first. Let's start with the that we have. Okay, so the first thing we have to install Docker. For that, we are going to search Docker on Google, and we're going to open the first link that we have. Then we are going to go over here and click Get Started. Now over here, it provides us with the options that we want to download for Mac Intel chip, Mac for the Apple chip, or we want to install it on Linux, or we want to install it on Windows. I have also provided links to videos in the slides, so you can follow that as well in case you have any trouble. Now, since I already have installed Docker on my Windows, I won't be going over it. What we have to do is simply click over here and it's going to download an installer which we have to run. It's very simple, like it is like downloading any other software that we install. There are some key things that we need to note over here, that once we open that installer, we need to check both of these commands on Windows. I'm talking about Windows. For the Mac and Linux system, you can check the videos. For the Windows system, you need to select both of these options that come: install required Windows components for WSL2 and add shortcut to desktop. Second one is optional, but I would recommend you do that. After installation, we are going to have this Docker desktop icon present on our desktop. And on opening that, we are going to see this screen, like get started with Docker in few easy steps. Now, in case you want to learn more about Docker, you can click start over here and see all the tutorial. Otherwise, you can skip the tutorial if you are only not interested in that. Okay. And after you open Docker, you're going to see this window over here. Since I have been using Docker, I see this kind of window over here, which is a little different from what we have. For new people who are installing ROS for first time, they are going to see this kind of image over here. Okay, so we have installed ROS and we have the ROS software running. Now, after running the ROS software, after we have double clicked, we need to open a Windows terminal. Now, for people who may not know what is a Windows terminal, it's just we simply need to go to the start menu and type in, we can either use a command prompt for that, or we can use a Windows terminal that we can download from the Windows store. So once we have this open, now we need to type in certain commands over here. So the first command that we need to provide is download a image. So let us discuss what is an image and what are the details for Docker. So just like GitHub, where people have uploaded codes and other different files on their own, we also have what is called a Docker Hub. There people provide images for people to download. Let's say we want, now for our example, we want to run ROS on Docker. So people have already provided the images for the same that we can directly install from Docker Hub and run them on our own computer. So we are going to first pull that image from the Docker Hub, and then we are going to run a container. Now the relation between image and container is something similar to the relation between a class and an object. A class is a blueprint of a structure and object is an instance of that class. Similarly, image is just a blueprint of how we want to run the behavior, and a container will be the actual instantiation of that image. So the first command that we need to type over here is, now this command Docker is just to check that Docker is running or not. Let's just run that and see if it is running. So we can directly conclude over here that Docker is running and we have the Docker installed as well. Okay. The next command that we need to type in is to pull the image from the Docker Hub, which is docker pull ROS desktop PNC noetic. So when we run this command, we are going to install the image on our computer. The loading screen is going to look something like this over here. Like it's going to download layer wise it's going to download the image layer wise, and once you have it downloaded, it's going to show us the command again. Okay, so now let's get to the actual part when we run the Docker container. For that, we need to type this command that is given over here, docker name. I'll just type the command and then we will discuss what it means. Okay, so the optional bit I would say over here is, okay, so you can directly copy this command, there won't be any issues. This name over here is kind of optional. We can either provide it or you can provide a different value over here. Like you can say ROS container, ROS tutorial, or any kind of alphanumeric thing over here. The rest of the things are mandatory and they should be written. So let's run this Docker container. Now on my computer, it's going to take slight more time than it is going to take on your computer, since I have the Google Meet running as well and we have this Docker running as well. So once we have this running, then we need to go to our browser and type in 127.0.0.1:6080. Once again, it's a little bit slow on my computer due to the Google Meet and everything running. So it's going to be a little faster on your computer. Okay, so the environment now we have over here is a Linux environment. So what, in a nutshell, what is happening? We are running, in very simple terms, we can say that we are running a Linux operating system on our browser. In very simple terms, we can say that. For the curious people, how it is working is that we have a Docker container running on our computer and it is communicating with the browser through VNC, virtual network computing. So just a thing to tell. Okay, once we are on this Linux environment, then we need to go over here. It's start menu.
Sir, can I interrupt you, please?
Mhm.
I want to ask one thing because I joined late. We are doing work on Linux on Windows, or means
We are working on Windows, but we are creating this Linux environment on a Windows.
yeah. Okay, thank you.
And from okay. Just I would say just try to ask it in the chat box from next time onwards if it is not that like difficult to explain, since it a lot of people would be there and asking through microphone, so it would get a bit difficult. Okay, so we have this start button over here, and then we click on System Tools, and then we go to Linux Terminal. So it's going to open a terminal in a Linux system. So let's see if I can increase the size. Okay, so the first command that we run whenever we install ROS, the first command that we should run, the hello world of ROS, is ROS core. So let's run that. And ROS core, as you can see, it is running perfectly fine. This means that ROS has been installed, like it is installed in this system and it is running correctly. Okay, so now for today's session, we are only going to run a little, like a small demo. First thing that we are going to run is the Gazebo simulator. Now the commands that I will be typing over here, you do not need to completely understand like what is we are typing. Just follow these and you may get the results that we have. We are going to discuss what these commands actually mean in the next sessions as such. So the first command that we have is ROS launch, Gazebo ROS empty world.launch. So we have run the command and now we are going to see a simulation over here. Since we have launched an empty simulation, we are going to see an empty 3D world. So we have this simulation over here. Since we ran the empty one, it's completely empty. So some things that you can try over here is add a block over here, add a sphere over here, and add a cylinder over here. So these are some of, you can try all these things that are given over here. They all do different kind of things as such. Okay, now this next thing that we're going to discuss is that usually in ROS, we have to run a lot of different programs. For that, we have to keep the terminal running as such. So we should not close the terminal that we have. Okay, so there is a question in the chat. I'll address that in a moment after I finish this. So we need to keep this tab running for the Gazebo simulation, and then we need to go over here. We click File, then we click New tab, and on New tab, then we need to type this command ROS run RViz. So once again, the commands don't need to understand what the commands are doing. We're simply going to run them for now. What this is going to do is launch the RViz application. RViz application is a software that is used to visualize the robot parts. Like we can visualize the robot model over here. If you know what are transforms, then we can also visualize transforms over here. We can also visualize the working of algorithms over here, and we can also visualize the sensor readings of the robot over here as well. For instance, if we go to this add button over here, then you can see that we can add a lot of things. Like we can see what the camera of a robot is seeing through this image. We can see what the laser scanning of the robot is detecting through this laser scan. And we also have this point cloud, which we can use to see the point cloud of the sensors that we have. And there are a lot of different things. You can experiment with them if you want. Like there is not much to experiment right now, but you can try and run both of these software to see how they work. Okay. So we have some questions in the chat. I'll just come to that as well. Okay. So once we are done with this, we are going to close them. Now for the, I won't say now. Okay. So I would now, ask you to try and replicate these instructions on your own when we are done with the sessions. As we said with this session, you are going to try this after this session. So to form a feedback loop for the same, so that you do the task and you have some motivation to do it, you should post this whatever you run by following the instructions. You have to post this as a social media post. You can be as creative as you want. How would you like to post it? You can either post an image, you can either post a GIF, or you can either post a video of the same. And you have to tag Robotics Club with it as well. So, and maybe we are going to introduce an assignment in the Google Classroom where you can submit the link to that post. The post that you have made, the best posts out of those will be reshared by Robotics Club as well. This is simply to get a feedback loop and you have some motivation to work on it as well. So all the instructions are in the slides. You can simply follow the slides and you can get all the work done. Also, once we are done with the all the work that we had, we can simply close this. Yes, and we're going to close this tab as well. Then we need to go to the Docker. Now the name that we typed over there, ROS tutorial, is going to appear over here. And what this green one means is that we have a container that is running. To stop this container, we need to press this stop button. And it's going to stop that container, and we are going to have a gray color over here now. Now, for the next time when you're going to run this same container, you do not need to go through the terminal commands that we discussed. From next time onwards, you can simply come at this Docker software and then press the start button. And then it is again going to start the container, and we can again go to 127.0.1 to access the Linux environment that we had. From next time onwards, it takes a slight more time. So you have to wait a little bit for it to load completely as such. And also you can delete this container if you want. If you delete this container, then you have to again type the terminal command that we discussed over here, like docker run command. If you delete this container, for now, I'm deleting this container and that's it. Okay. And as I said, you have to replicate the instruction and post it on social media. For the next session, we are going to simulate a TurtleBot 3 robot in the Gazebo and see how it works. So yeah, this is it that we had for this session, and now we are now open for questions. If you have any questions, you can ask. And there are already questions over here, so we will answer that. If we have WSL2 installed with ROS2 Nomadic, do we have to need to follow the installation steps? Now, the instructions that are discussed over here were completely for a new person that is entering this ROS and learning ROS for the first time. Now, installing ROS, I think you may also know that installing ROS is very time consuming, and we have to run a lot of different commands over there. This is by far which I feel the simplest way to get started with ROS and install ROS. If you have installed ROS or you have Ubuntu and you want to try the native installation of ROS, then you're free to do that. This is just the instructions that I have shown over here is for someone who is starting out with ROS and they do not want to follow the installation as such and learn more about ROS. Is there any difference between Gazebo and RViz? Gazebo was the window simulation window that we opened before, and the one that we opened second time, this one is the RViz window. So Gazebo is a physics simulator. We can simulate how the robot is going to behave when it is moving, when it is going to collide with other objects, and so on. We can simulate all these things in a Gazebo simulator, which we have over here. The RViz simulator is just a visualizer, and we can use that for debugging our robotics applications. Like we can see what the laser scan is seeing. Like for instance, in Gazebo, we cannot see what the laser values are outputting. But in RViz, we can visually see what the laser values are, where they are actually colliding and returning back. We can see the point clouds in RViz. We can even see the robot model. We can see the transforms that we have in RViz, but we cannot do all of this in Gazebo. So Gazebo is a physics simulator, and RViz is a visualizer. That is the main difference between Gazebo and RViz. I using a window, I need to install Docker or run it natively. And for Aryan asks that do I need to install Docker or run it natively? He is already using Ubuntu. The answer to this is similar. Like if you want to follow the instructions for the official instructions to download ROS, then you're free to do that. But if you want to avoid the installation of ROS as such, then you are free to use Docker. It's your choice. You can run both of them. How can we open ROS on Docker? Hitesh, could you elaborate on that? Like what do you like? ROS is just the commands that we run. So how can we open that? I have installed ROS2 Galactic on Ubuntu. I was not able to replicate ROS launch. Okay. So Arnav asks that, sir, I have installed ROS2 Galactic on Ubuntu and I was not able to replicate ROS launch, ROS run. You demonstrated. Now for ROS2, the commands are different. For ROS2, like for instance over here, like ROS launch, the command is ROS2 space launch, and then the other thing actually happens. Now there is a slight conventional difference. Conventional difference between how we call the different commands in ROS1 and ROS2. So that's why the commands that you ran, ROS launch and ROS run, did not run in ROS2. But if you run these commands in ROS1, then they are going to work. And for this series, we are actually following ROS1. ROS2 will be discussed later in the sessions. So the commands for those are different. That's why it run. Okay. Yes. So Soumyadeep asks, RViz helps to visualize the signals received by the sensors, right? Yes, it helps us to visualize the signals that are received by the sensors. Not only that, it allows us to visualize a lot more things than simply sensors as such. So Hitesh asks, is ROS a language or a software? It is a set of softwares. It is not a single software. It is a set of different softwares that helps to create robot software. If it is a software, how can we open it on Docker? So on Docker, we are actually opening a Linux system. We are not opening ROS on the Docker. We are starting or opening a Linux system on Docker. And on that Linux system, ROS is already installed. Hence, we do not go over the installation of ROS. We simply just open that Linux environment and start using ROS. That's what's happening. In the past, I have worked on the ROS software using. Okay. So Manish asks, in past, I have worked on ROS Development Studio provided by the Construct Academy. It didn't require Docker. Can you please specify what software they are using? So first, let us clarify for people who don't know what is the Construct Academy. So the Construct Academy is a company that provides us where we can where we can develop robot software and learn ROS online. Like over here, we installed Docker and then we ran this on a browser. On the Construct Academy, it is quite simple. I would say even simpler than this, that we go to the Construct Academy website. We just log in over there and we have the different systems that are running ROS. Like now, okay. You can try that on your own. For people who are interested, you can go to the Construct Academy ROS Development Studio and they can try how it looks. Like it provides us with different tools that we can open a terminal, we can edit the code files, we can open the simulators and so on. Why we are not using the Construct Academy over here is the Construct Academy is good to use, but I think we would be able to learn better if we actually have a Linux kind of environment where we are using ROS. So that's the reason we are not going over that. For people interested, can go to the Construct Academy for the same. They can check it out. So Arnam asks, so can I install ROS along with ROS 2? Yes, we can install ROS along with ROS 2. Both of them are compatible side by side. We can have both of these systems installed on our computer. You just need to check which ROS version you have to use. If you are on Ubuntu or on a specific Ubuntu version, for that specific version, you need to install that specific ROS. For our sessions, we are using ROS Noetic. Out of topic, but I have an article about how to run ROS to Noetic on Windows using WSL2. Okay. Can you briefly tell me to install till ROS with Docker? Okay. So Nidhi asks that, can you briefly tell me to install till ROS with Docker? So, okay, I'll just briefly go over it. What you need to do, the slides are present over, these slides will be given to you so you can check the instructions. You just need to go to the Docker website. You need to click get started over here. Then you need to install the installer for Windows. On opening the installer, there is going to be certain instructions. We need to tick these both boxes which says install required Windows components for WSL2 and add shortcut to desktop. We need to select both of these options. Then we have the Docker. After that, we would have the Docker desktop icon on our desktop. Then we need to start that Docker software. And we would see a screen over here if you are installing it for the first time. Then you need to go open a terminal or a command prompt on your Windows system and then type in this command docker pull period ROS desktop vnc noetic. It's going to install a ROS noetic image which we can run. Then we need to type the command docker run this ROS tutorial, all this complete command, and then it is going to start that Docker container. Then we can go to the browser and go to this link 127.0.0.1 and then we can start working with ROS. Over there we can open the terminal, instructions are given, so you can try that. Okay. Ali says, like, please provide us with class schedule, and okay, so I think Robotics Club will be able to answer that. We will be providing that as such. So Tanmay asks, sir, what language do we need to know for working in ROS and what level we should be on it? Okay. For this session, we are only going to use Python and that too very minimal. Like, we are not going to use very big constructs like classes and objects and so on. It's going to be really simple code like for loops, if and else and so on. And importing some libraries and so on. We're only going to use Python for this session, but if you're looking to develop for real robots, then you should learn C++. That is the way to go. Okay, Aryan asks, sir, how much space required on drive for Docker and for image? So, actually it requires a good amount of, I don't know exactly how much it requires, but you should have a good amount of memory available. For instance, this ROS image is of 5 GB. So it's not completely of 5 GB. It's a slightly lesser than what it will be installed on your computer. So it says 5 GB over here. And the Docker software itself, the Docker software itself is a bit lighter, but the images can be very large. So yeah. Can Linux potentially crash while working with ROS? If yes, what can be done? So Hitesh asks, can Linux potentially crash while working with ROS? If yes, then what can be done? I would say I have never really experienced like crashing like while working with ROS. The Linux has crashed, so I don't know. I won't be able to like answer that pretty well because I have not experienced any time that Linux has crashed while working with ROS. If this happens on your on this Docker kind of container, you can simply stop the Docker container and rerun it again, or delete the container and rerun it again. So that what can be done. But and Soumyadeep asked, but sir, what about those who don't know Python? Okay. You on like for the Python, let's see. Okay. You for the program, like we are not going to do a lot of programming in this course as such. There is, I think, we have planned like 1 or 2 programming things that will be in this, and they are two very light. So you do not need to know any programming language as such. We are just using ROS and trying to run it in these sessions. So code related things are not going to be that much. For you just need to know how to code. Like you should know the if else statements as such, like what are if else, what is for loop, what is while loop, and what is importing libraries and so on. So not knowing Python is also okay with this course. Okay. So I guess we can take questions for 5 minutes more. And if you have any questions, I'm here for 5 minutes more. Otherwise, the session is complete. You have to do that social media posting assignment. And in the next session, we are going to simulate the Turtlebot 3 robot. So yeah. So Ashwin asks that, can ROS handle time sensitive or real time tasks? Actually, ROS has this drawback of not being able to be used in real time. ROS 2 actually solves this problem. It is better compared to ROS in terms of real time things. Now, I have personally, I haven't actually worked with real robots as such, like how it is, like how it works in real time, what are the various issues and so on. But what I have learned as such, what I have read is that ROS compared to ROS 2 is better while we are doing this real time tasks. And ROS 2 is also really good for industry. Like it is very industry ready kind of thing. We can directly deploy ROS 2 systems. For ROS, we have to make few changes before we actually deploy it in real systems. So yeah, ROS 2 is better for handling real time tasks. Okay, Arnav asks, ROS distro was set to Galactic before. Please make sure that the environment does not mix paths from different distributions. It was showing. Yes, you can proceed. Like when you want to work with ROS Galactic, then you need to set this environment variable ROS distro to Galactic. When you want to work with ROS Noetic, then you have to set this environment variable to ROS distro Noetic. That is what you have to do, like that. Like you should not be running like you should not be running them, both of them, to like, we can have two separate terminals that is running ROS Noetic, one other one is running ROS Galactic, but we should not have it in the same terminal as such. That is the thing. Also, if you are like interested about reading more about it, you can also Google it as well. It's a well-known thing that people do, like installing ROS with ROS 2. It's a well-known thing that people do. And then ROS does not have any benefits compared to ROS 2 other than being well documented and having an informative community. Okay. Prakhar asks that, does ROS have any benefits as compared to ROS 2 other than being well documented and having an informative community? Yes, that is the main benefit that ROS has compared to ROS 2. We like what I have seen is that ROS 2, like many different software ROS packages, have not yet been completely or fully imported to ROS 2, and even the tutorials that you find may even be somewhat incomplete and you may face errors while doing that. For ROS, it does not actually really happen much. Everything is well developed and the tutorials are good. So this is the this is the major benefit that ROS provides compared to ROS 2. Otherwise, for if you're working on building robots and if industry based things, then ROS 2 is actually preferred since it takes into account the drawbacks of ROS and has an improved one. So for learning, I would say we can start with ROS and then shift our attention to ROS 2. That should be like the path. Okay. Will we be able to build robot brains after this series, and what level will be on after this series? Yes, I would say that you would be able to build the robot brains, not from scratch, but you will be able to build them using ROS packages. Now, what I have planned is in the next coming sessions, we are going to work with mobile robots, robot arm manipulator robots, and even quadruped robots. So you would be able to design their brain, but not, I would say, directly from scratch, like having every piece of software written by our own. We are going to use ROS packages for the same. So after this series, you would be able to use ROS well. Yeah, your understanding of ROS will be better if if you are a beginner for ROS, then you will be able to understand ROS and what are the different components and so on. Okay, so I've now installed ROS Noetic. Tanmay asks, how do people control robots with mobile? Okay. Now there can be various different techniques that we can use. We can either use Bluetooth or we can either use Wi-Fi. Like on a robot, we can have like a Bluetooth device, Bluetooth device, and from our phone we can connect it to the Bluetooth device. Then we need to just parse the commands that are coming in from the mobile through the wireless system, and after parsing we can send those commands to the robot motors. Similar thing can happen for Wi-Fi as well. We can connect these two systems and the mobile is going to send some signals. Now they can be encoded signals. Any system that is present on your robot can decipher that command and then command the motors ahead that how it needs to do its task. I would say that robots that are controlled with mobile, they are like robots that are controlled with remotes. So it's kind of like they are primitive kind of robots. We are controlling them. The robots should be able to function autonomously. So that is also thing. For robots, to control robots with mobile, like Bluetooth and Wi-Fi, they are usually used, as I have seen. How can we control by computer vision any soft? Nidhi, can you ask, like, I did not understand this question. How can we control by computer vision any software image processing? Okay. Okay. So so your question is that how can we control a robot by computer vision or image processing, right? Okay. So now computer vision only forms a part of the robot. There are other systems as well, like yes, there are other systems as well, like we discussed. There is also a motion planning system. What image processing is going to do, like if we have, let's say we have this bottle in the environment, and and our robot is present at the camera over here, like we can see. So the image processing or computer vision algorithm is going to tell how much distance apart is this bottle from the camera or from the robot. Then it is going to pass these coordinates to the robot, and the robot is going to use different motion planning and control algorithms to actually tell where the robot needs to go, something like that. It doesn't actually directly control robot, it's just a part of the complete robot system. Also, since you are asking like how can we control computer vision, yes, RRT or D star, like these are commonly used algorithms for path planning. Since you're asking like if you want to like learn more about it, there are also techniques called visual servoing. In that they directly use deep learning to like they build a system. They do not want to build other systems, they directly build a system, deep learning based system, that takes an image from the camera and tries to learn a function that will directly make the robot go to that object that is present over there. So we do not need to write a lot of code, but we need to write a good architecture for doing that in deep learning as such. So what should I follow? If you know deep learning, then you can try that. But if for SLAM, can we follow? Okay. Like for SLAM, I haven't seen from what I have seen, I haven't seen SLAM being used directly through deep learning, like something like visual servoing. I haven't directly seen it with SLAM. With SLAM, I have seen like the perception part is done using deep learning, and then a further algorithm is written that does the SLAM things as such. So there is not a complete one-to-one system, but there is a system after image processing that does the SLAM. That is what I have seen. So you cannot directly do that thing in this. Like there may exist techniques, but I haven't seen any such for as of now.
Yeah, so there are no more questions. Okay.
Any idea for detailed study? You can check this algorithm Chimera View. I know, like, I think I have only, like, research wise, I have only studied this algorithm Chimera View as such. You can try this out.